Today we get into chapter 8, which is on linear momentum and collisions. And so it gets into sports. There's, of course, the requisite overproduced OpenStax video. And it's just all about football. So American football, in which these guys, maybe we need to turn down the volume a little, oh my God. So it does tell you that, yeah, a football player running has a momentum, which is mass times velocity. And if they collide, there's something about crushing bones. If they collide, then you say that the momentum before and after the collision is conserved, whether they stick together or whether they bounce apart. It, of course, then starts talking about players getting injured and sustaining bad head injuries. But then it sort of indicates that somehow this is all worth it so that the screaming fans will jump to their feet. So anyway, it's once again, this book is from Rice University in Houston, Texas, and you can kind of see that there's a bit of that culture coming through. So let's just ignore that. And we'll go on to section 8.1, linear momentum. So what have we sum up here? We've got force in newtons. We've got energy in joules, which comes from this work, force times distance. And now we've got a whole thing called momentum. So momentum, it's sort of like energy in the sense that an object can have momentum. It's unlike energy in that momentum is a vector. So remember, energy is a scalar quantity. It doesn't have any direction, but momentum has direction. So it's the velocity of an object multiplied times its mass. So that's our definition. So very, very simple definition. The units are kilograms times meters per second. There's a couple of examples of that. But this is the really interesting thing, and this is actually the way that Isaac Newton first wrote down his second law, which was that the net force is the change, the time rate of change of the momentum. So he defined momentum, P, and then said delta P divided by delta T is the net force. So it's really a derivative, the time derivative of the momentum. But the way you can sort of see this is that delta P, if the mass doesn't change, it's just m times delta V. And remember, delta V divided by delta T is acceleration. So like the change in velocity divided by the change in time is the acceleration. So this becomes F net equals ma. Same thing, which, that's Newton's second law. Section 8.2 introduces the change in momentum is called the impulse. So this is the equation right here. Sometimes people call this the impulse momentum theorem, but delta P, the change in momentum, equals the net force multiplied by the time. So it's really just a rearrangement of that equation from the previous section. But we give F net times delta T a name called the impulse. And the examples are just showing one interesting thing is that all of these equations, they're vector equations. Delta P is a vector. The net force is a vector. So really, in two dimensions, this equation 8.18 becomes two equations. It's delta Px equals F net x times delta T, and delta Py times F net y times delta T. So there's some examples of that. The other thing is the impulse when the force is changing, net force is changing, is the area under the net force versus time curve. So usually the force during an impact or something, during an impulse, goes up and then goes back down to zero. And if you calculate that area, you get the average, the effective force is kind of like the halfway point between the maximum and the bottom. So the area of this rectangle, F effective times delta T, is the same as the area of the actual curve here. So it's actually an integral. Section 8.3 introduces conservation of momentum. This is similar to conservation of energy. For a lot of systems, the energy before and after is the same. For a lot of systems, the momentum before and after is the same. So they talk about consider what happens if one car bumps into another. So what's going on is this guy M1 crashes into M2. There's a lot of collisions in this chapter for some reason. You say the system of interest is both cars. And in that case, the external forces during this collision are kind of negligible. So you've got a big forward force on M2, you've got a big backward force on M1 because they're equal and opposite forces during this collision. So there's no net force on the system during that collision, and so there's no change in momentum. So that's when you would say P1 plus P2, for example, is constant. You've got the initial and final P1 plus P2 are the same. And here, instead of using finals and initials, they use P1, P2 as the initial, and then P1 prime and P2 prime as the final. We often use primes to denote the final state. P total initial is P total final. And you can see that's pretty similar to that E initial equals E final conservation of energy from back in chapter 7. So an isolated system is defined to be one for which the net external force is zero or negligible for some reason. And in that case, that's when you get that for that system, if there's no external force, the momentum is conserved. And it often happens during some sort of a collision or some sort of an explosion. We talk about subatomic collisions. And lastly, they combine the conservation of momentum with conservation of energy to get elastic collisions in one dimension. So there's a definition here. An elastic collision is one that conserves kinetic energy. So we would say any collision conserves momentum because the forces between the two objects are much bigger than any external forces during the collision. An elastic collision is one where the kinetic energy before and after is the same as well. So you end up with two equations here for an elastic collision. One is the momentum before and after is the same, and the other is that the energy before and after is the same. And they look similar, but one has mv's and the other one has mv squareds. And so there are two equations, and there's sort of two unknowns, which is the final velocities. So it takes a little bit of work, but you can combine these equations and solve for v2 prime and v1 prime, the final speeds of the two particles, inelastic collisions in one dimension. So we have talked about elastic collisions in which the kinetic energy before of all the parts is the same as the kinetic energy after of all the parts. But in real life, that very rarely happens. There are lots of ways that energy can be used up during a collision, such as internal friction or damage of the two objects. Energy usually gets taken away. So most collisions, they still conserve momentum because the external forces are negligible, but the internal kinetic energy changes, so it's not conserved. That's called an inelastic collision. And there are several subcategories of inelastic collisions. The first one is a perfectly inelastic collision. That is a collision in which the objects stick together. So they have no relative motion afterwards. So they're both moving, they hit each other, and then they're stuck together. So that always involves a big decrease in the kinetic energy, but the defining feature of a perfectly inelastic collision is just that they're stuck together after. And example 8.5 calculates that. So this is a perfectly inelastic collision because the goalie catches the puck here. So they end up with sort of stuck together, right? Same velocity. And you can actually calculate the initial kinetic energy and the final kinetic energy, internal, I guess is what this means. And you get that the difference, final minus initial, is negative 91.7 joules. So there's been a decrease in kinetic energy. There's another example here of a third category of inelastic collisions in which the kinetic energy increases. So it's kind of strange, but they tell you the recoil velocity, and so you can calculate by conservation of momentum all the velocities. And here you find that the final kinetic energy is bigger than the initial kinetic energy. So what happened is that when they collided, there was some potential energy stored in a spring, and then something about the collision triggered that spring to release its energy. And so this is sometimes I call it an explosive collision, because you've triggered something to release, often chemical potential energy, or in this case, spring potential energy. So section 8.6 goes to 2 dimensions. So, and basically it's just reminding you here that this conservation of energy equation is a vector equation. So really it's just 2 equations, which is that the x component of the momentum is conserved before and after, and the y component is conserved before and after. So they put the ticky things on for after, no ticky things for before, and there's an x here, and then there's also a y. So this is conservation of momentum along the x-axis, the x components, and then there's conservation of momentum along the y-axis. There's the y components for these collisions. So you work all this out, and you can get some of the angles for collisions in sort of a 2D plane. I'll talk about that a bit in class. And the last section of chapter 8 is called an introduction to rocket propulsion. And again, I'll talk about this a little bit in class because they really just sort of state that when a rocket is accelerating straight up, you can have a good approximation for the acceleration of the rocket. It's all this stuff, delta m over delta t. M is actually how much, I guess, of the hot rocket gas is ejected out the bottom. And m is the mass of the rocket. T is, I guess, delta m over delta t is the rate that exhaust is ejected. And VE is the velocity of the gases relative to the rocket. And so this gives you an acceleration minus g, because there's also gravity, and then you can go straight up into space. So kind of a useful equation. And that is it for chapter 8. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom, where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.